Now, yes, we can see. Yes.
Hello, everyone. I would like to begin by thanking the organizer of this wonderful opportunity to present my speech. My name is Amal Sila, and I am PhD student at University Mohammed Boudiaf in Sila, Algeria. Today, we will present simulation and design of wideband and height isolation GYSEL power divider for wireless communication application. As an outline, we'll begin by exploring the concept of power divider, delving into their various types and their application in different fields. Next, we will present the design and simulation of GYSEL power divider using CST simulation. Finally, we will analyze the result obtained from the CST simulation of the proposed design. Then we will present a conclusion of this discussion. Evaluation of power dividers market. The global RF power dividers market size was valued at $10 million in 2021 and is projected to reach $40 million by 2013, as shown in Figure 1. The need to split or combine signal is essential in modern RF design in variety of applications, including Internet of Things, digital communication, and automotive driver assistance. The importance of power dividers. In recent years, with the rapid development of wireless communication system, many ideas and technologies have been applied to improve the overall performance of the system. Passive power dividers as essential component of RF model have attracted more and more interest in researching and industry field. In microwave system is often to need to distribute radio frequency power to various paths for different applications. The easiest way to perform this operation is by employing power divider circuit. What is power divider? Power divider, also called by power splitter, are one of the essential components in various communication systems, including feeding network of antenna array, balanced amplifier, frequency multiplier, etc. A basic power divider is a three-port device is used to divide or combine power, as shown in Figure 3. As mentioned, a power divider is a three-port device. A three-port device can be not lossless, reciprocal, and the height isolation port at the same time. Therefore, in order to design a power divider, any of this condition therefore, in order to design power dividers, any of these conditions have not accepted. The two main topologies that are widely used in power dividers is Wilkinson and GYSEL power divider. Classification of power dividers with different frequency configuration like dual band, multi-band, wideband, power divider with equal or unequal power division, in phase or out of phase power divider, and reconfigurable power divider, etc. GYSEL power divider. A GYSEL power divider is an electronic circuit designing to divide power and distribute it equally among two or more output ports. One of the key advantages of this type is high power handling capability. This is achieved thanks to the use of the external isolation resistor, as shown in Figure 4. In this section, we will showcase practical examples of GYSEL power divider achieving both wideband operation and height isolation. Now we will show the design and simulation of GYSEL power divider using CST simulation. Figure 6 shows a schematic diagram of the proposed design. The proposed divider is a three-port device that consists of 6 transmission lines and 2 isolation resistors to dissipate power. Using computer simulation technology, CST software, a powerful tool for simulating microwave circuits, we will implement the GYSEL power dividers in the previous figure, as shown in Figure 7. The GYSEL power dividers was designed on Rogers substrate with electrical constant of 3.55 and thickness H about 0.508 millimeter with loss 0.0027. Result and analysis. In this section, we will analyze the simulation performance of the GYSEL power divider design using CSC simulator and MATLAB simulator. The simulation results indicate a wide bandwidth of operation ranging from 3.5 gigahertz to 3.6 gigahertz. Within this frequency range, both the input return loss S11 and output return losses S22 and S33 are better than minus 25 dB. This significates good signal matching between the divider and connected device. The isolation between the output port represented by the S23. The S23 parameter is greater than minus 35 dB across the bandwidth. The last figure depicts the transmission coefficient S21 and S31. This coefficient represents the power transfer from the input to output 2 and 3 respectively. At the operation frequency of 3.5 gigahertz, both S21 and S31 are better than minus 3.5 dB. Overall, the CSC simulation results demonstrate that the proposed design achieve a wide operation bandwidth, good signal matching, high isolation between output, and efficient signal transmission at 3.5 gigahertz. In conclusion, the future of power dividers regarding the operation frequency band, input output return loss, and isolation between the output parts will significantly affect the overall performance of the communication system. The objective of our work was to design a novel GYSEL power divider achieving both wideband operation and high isolation. The proposed design is simulated using computer simulation technology CST software to analyze its S parameters. MATLAB may be used for further data processing after the CST simulation. As perspective, this project could be further improved by designing the same circuit with open short step for dual band operation or for power dividers with the arbitrary power split ratio. In this section, in the end, we will provide a list of references used through this presentation. Thank you very much for your attention.
Thank you for your presentation. If there are questions about it. If not, thank you again. And the last paper from our session is from Milutinov Miodrag, measurement of AC and DC magnetic field reduction.
Hello, can you hear me?
Yes.
Okay.
And you can hear, we can see your screen.
Oh, wonderful. Just to start presentation. Yeah, it's okay, yeah?
Yes, yes, yes.
Okay. Well, my name is Miodrag Milutinov, and I come from Novi Sad, University of Novi Sad, and I'm glad we will end on the time, I think, at 3 p.m. Yeah? I'll do my best to be short as possible. I saw all your papers, wonderful papers, deal with electrical cars and bus and other things. We try to analyze the, let's say, electromagnetic compatibility or maybe some possible magnetic field reduction of currents, DC or AC currents. This is one, let's say, pilot measurement. You will see. I will explain why we start with this type of measurement, and at the end I will say what is our further research interest. So first of all, the motivation of this type of measurement. Our younger colleague 3 years ago started with these calculations about magnetic field reduction of different material enclosure copper conductor, as you can see on this slide, and we just now try to make some measurement setup, some let's say workbench test to try to measure and to find out maybe some correlation between calculation and measurement. So this is what we made, this wooden support. So this is like our setup for verification. And you can see in the middle of that tube is one wooden support for the one wire, thin wire copper. But that wire can handle the 40 amps of DC, so it's thin enough. We use 40 amps for DC current and 20 amps for AC current at frequency of 50 hertz. And of course, you can see the metallic tubes that we used for that shielding. So we need a power supply for that experiment. We use the powerful DC current source with some resistor box just to control the current by measuring the voltage. And this is, you can see on that figure on the center of the screen. And on the right one, you can see the AC current source, which has integrated ampermeter. So let's say it was easier and more accurate to set up that current that we need. Here you can see the measurement equipment. We use two instruments, one for DC magnetic field, one for AC magnetic field. At the upper photo figure, you can see in the right side of the figure, you can see the let's say old but good enough, still good enough Bell 64 incremental Gauss meter. And with this XR probe that you can see here, which is very sensitive, we can set up the lowest range scale down to the 10 microtesla with 0.1 microtesla resolution, which is good enough for this kind of measurement. And for the AC magnetic field, we have a modern instrument from the NARDA EFE 300 with one small probe, small enough to capture the magnetic field at, let's say, at the point, and also very good range with very good sensitivity and resolution. So here we can see that method of our measurement. Once again, our source was a wire of 1 meter in length. The metallic tubes are a little shorter, about 80 centimeters in length. And we have two different radius of the tubes, smaller and little bigger. And we use we combine that tubes. You will see later. So here is one meter long wooden scale oriented perpendicular to the tube, just to fix that measurement point, to be sure that we measure as we calculated. So the starting point of that scale was at the outer shell of the tube, and we measure at each 10 centimeter further from the tube. And we also we measure also only vertical space component of the magnetic field, because in that plane of measurement we expected only vertical component of the magnetic field by the theory. So this is the procedure. First of all, we measure the background DC background field without any current source. just to later we can find the actual source, which is produced only by the current source. After that, we turn on the source and measure DC field first without metallic tubes, just to compare with the theoretical expectation, and after that we put one metallic tube, first of copper, second of aluminum, and third it's like zinc iron, how to say, how to galvanize steel, something like that. And after that we tried all combination to find out the best combination, and once again to compare with earlier analytical and numerical calculations. For the AC field, we didn't need to measure background field, only that without tubes, and all that combination of single and double metallic tubes. Okay, here you can see the first results. The red line on that diagram present analytical calculations that this is derived from Biot-Savart law, taking into account the finite length on our wire. The black one is a measured results, which is good aligned with that analytical calculations that we expected, of course, and numerical calculations are performed using some package software, finite element method, and it's a little bit higher, you can see, because it assumed that the wire is infinitely long, so it's another expression. So it is something that we expected. This is the results of DC magnetic field. On the left side, measured results. On the right side, calculations. COMSOL, this is that package that we use, give us the same results for any type of shield. So I think we almost didn't expect that will be some reduction, and this on the left side measurement just approved that for DC magnetic field we cannot expect such reduction, especially if we use copper or aluminum. Maybe galvanized steel will be introduce some reduction, but it's not good enough or not thin enough. Maybe this is the reason. This is the results of AC magnetic field. On the right side, once again, this is the calculations, and of course, calculations results strongly depends on your model, and we assume that the model is infinitely long. Also depends of the parameters you put in, such as permittivity, permeability, conductivity. And on the left side, this is the measurement that we obtain. First, on the first that we first saw is different. We didn't expect such a different, but lately we figure out why is that we probably the length of the shield and the parameters, such as especially conductivity and permeability, is not as we use in our model. So it's good to measure to see how much you can expect different from the model that we usually used for our investigations. And here we just take out one of these measurement of the previous slide. We just compare for one tube of, let's say, high permeability material, and we can see that that material introduce some reduction that is better than the calculation, and that is something that we have expected. But on the right side, we expected that the copper together with the galvanized steel will introduce the expected reduction, such as red line, but they didn't reduce the field. So this is something that we maybe didn't expect on the first time. And once again, we find out the reason of this discrepancy is in the finite length of our tubes, and possible the permeability and conductivity of our materials is different that we use in our model. So this is something that we conclude after all that measurement. And at the end, I will say that this is our first step of our investigation, and our further work that we will expect more reductions is with metallic shields of different shape and size, like in this slide you can see. But first of all, we would like to take measurement with, let's say, whole tubes before we cut them, and proceed with the next step of our investigation. So that's all. That's all. Thank you for your attention.
Thank you for your presentation. And if there are questions about it, please. Okay, nobody?
Yes.
Yes?
Yes. I don't have any question, but I would like to put a comment on this. According to the first diagrams Professor Milutinov showed in this paper, in this presentation, there is no influence of any kind of, let's say, shielding material or shielding thickness on magnetic field reduction, DC magnetic field reduction. Well, nowadays we have more and more DC magnetic field. We have time constant magnetic field, and we have time varying DC magnetic field, which of course, which is produced by DC currents from, let's say, the sources of renewable energy from photovoltaic systems, with storage, DC storage energy in batteries, different type of batteries, in electric vehicles. So the DC magnetic field is more and more present in our days nowadays. So it is very important to understand, to notice that this is very, very difficult to reduce DC magnetic field. AC magnetic field is much easier to reduce due to eddy currents, to induce currents inside the conducting materials. But here there's no eddy currents, so the only possibility is to reduce this with shielding systems, is to apply a material with very, very high relative permeability and very thick material. We tried the calculation, just proved. The calculation proved it. We tried the calculation with the HyperSeal 5 with the relative permeability of about 80,000. And we try the thickness of material up to 5 centimeters or up to 10 centimeters even, and then we reached some reduction of magnetic field. So it has to be noticed that it is very, very difficult to, it is important to reduce the field, especially inside the car, the electric vehicle, but it is very difficult to reduce it on values defined by standards. So we have to take into account all this with the next approaches to use of to application of DC currents in our world. That's my comment, little comment to add in this presentation.
Thank you, Professor.
Thank you. Thank you. Is any other question? No, then we will see on the round table. I hope so, that you have time to refresh and to see you in the round table. Wish you all the best.
Bye.
Bye.